Welcome back to the Deep Dive. Today we are undertaking a fascinating journey, starting way up in the realm of pure theoretical physics, the elegant math of invisible electric fields. And we're going to end up right down on your circuit board.
Exactly. Right down in the messy, high-stakes world of real electronic components.
And that's really the mission, isn't it? We're connecting the dots between this foundational law, Gauss's law, and the surprising, sometimes even explosive realities of hardware.
That's right. We've pulled together everything from university physics notes to some pretty gritty component data sheets and reliability studies to do it.
We want to give you that shortcut to knowledge, to really understand how fundamental physics dictates everything from, a safety warning on a component to a circuit's entire expected lifetime.
Yeah, we're showing you how these invisible fields are quantified, how they're managed, and sometimes how they're completely ignored, which can lead to some pretty catastrophic results.
Okay, so let's start at the very beginning of the field, pun intended, I guess.
Right. Let's start with the most powerful concept in electrostatics, Gauss's law.
Okay, let's unpack this. It all begins with the idea of electric flux, which is written as DOSF with the subscript E. For anyone who hasn't seen this since college, how should they, visualize it?
Think of it like water flowing through a net. Electric flux is basically just a measure of the electric field that's passing through some surface.
Okay.
But, and this is the key, Gauss's law only really cares about a closed surface, something physicists call a Gaussian surface.
And that surface can be real, like a metal box, or it can be completely imaginary, right? Just something we draw for the calculation.
Exactly. And the reason Gauss's law is so incredibly powerful is its beautiful simplicity.
What's the core insight here? What's the big reveal?
The big conceptual leap is this. The net electric flux through any closed surface depends only on the net electric charge, the QN, that's located inside that surface.
And that's it.
That's it. It doesn't matter if the surface is a perfect sphere or, a crumpled piece of foil. If you enclose 5 coulombs of charge, you get a fixed amount of flux coming out. The shape is just irrelevant.
And that relationship is fixed by a constant, the permittivity of free space, epsilon naught. So the formula is simply flux equals the charge inside divided by that constant.
Yep. Pure universal physics. Now, actually calculating the electric field, the E field, directly from this law, well, it really only works if the charge distribution has a high degree of symmetry.
But when it works...
So when it works, it turns a really difficult calculus problem into simple high school algebra.
This is that elegance you mentioned. So if you have a single point charge, you just imagine a perfect sphere around it.
You got it.
And if you have a long charged wire, you'd use a cylinder. You're matching the Gaussian surface to the source's own symmetry.
And the results you get from that show how profoundly geometry dictates physical reality. For a simple point charge, Gauss's law instantly gives you Coulomb's law. The field strength drops off by the inverse square of the distance.
So you double the distance the field strength orders. It gets weak fast.
Very fast. But if you do the same calculation for an infinitely long charged wire...
What happens then?
The field drops off much more slowly. It's just inversely proportional to the distance, 1 over r. And for a uniformly charged infinite plane like a giant metal plate, the electric field is uniform. It doesn't depend on the distance at all.
Wow. So that geometric difference completely changes the rules of engagement for the field.
Completely. And here's a quick nugget that really shows the power of this. Because the law ties the field lines directly to the charge, you can use it as a purely algebraic tool to solve puzzles about unknown charges.
Right, like those classic problems where you have, say, 3 unknown charges nested inside 3 different boxes.
Exactly. The source material has those. By knowing the total flux coming out of each box, you can set up a system of linear equations. 3 unknowns, 3 equations, and you can solve for each individual charge. No calculus needed.
It's basically saying, I can count how many field lines are escaping this volume, so I can tell you exactly what kind of particle is inside.
Precisely. If the net flux is plus E over epsilon naught, you know you've got a proton in your box. It transforms the invisible into a solvable equation.
Okay, so that's the theory. It's beautiful, it's pure. But let's be honest, those perfect frictionless spheres only exist in a vacuum.
Right.
What happens when we introduce actual physical stuff? The plastic and ceramic and gunk we actually build things with?
That is the perfect transition point. This is where the concept of permittivity steps in. Permittivity, written as epsilon, is the physical quantity that tells you how much resistance a material offers to the formation of an electric field inside of it.
So it's a resistance to field formation. Its unit is farads per meter.
Mhm.
And the vacuum permittivity, epsilon naught, that's the absolute baseline, the lowest possible resistance.
Exactly. But for electronics, what we really care about is relative permittivity, epsilon r. It's also often called the dielectric constant, or K.
And that's just the ratio of the material's permittivity to the vacuums.
Yep. And that ratio tells us exactly how much the electric force between two charges is reduced when you put them inside that material compared to what they'd feel in a vacuum.
So if I have a material with a dielectric constant of 10, the force between two charges inside it is literally 1/10 of what it would be in the air. The material is kind of shielding the charges from each other.
It is. And that ability to suppress or contain the field is absolutely critical. That is exactly what allows us to store charge efficiently in capacitors.
Okay, before we dive headfirst into capacitors, let's quickly anchor this in the macroscopic world. The flow of charges we can actually measure.
Right, we need to shift from static charges to current.
So current I is just the rate of charge flow. It's measured in amperes, which is 1 coulomb of charge flowing past a point every second. And the flow is governed by Ohm's law.
V equals IR.
I always think of resistance like friction on a highway. Voltage is the pressure pushing the cars, and resistance is how narrow the road is.
That's a great analogy. The higher the resistance, the harder it is for current to flow. And that resistance costs us something. It creates power dissipation.
Right. Power P. The rate energy is transferred or dissipated, measured in watts.
And the key formulas here are the ones with resistance, like P equals I squared R, because that I squared R is almost always just wasted energy that shows up as heat.
And that heat, that's going to be a crucial villain in our story when we get to real-world capacitor flaws.
It's a killer.
Just as a quick practical aside, the source material reminds us that resistance is still often encoded with color bands, that old IEC standard. Like green, blue, red, gold is 5.6 kilons, 5% tolerance.
The abstract physics eventually gives way to a color code,
Yeah.
which brings us to the component where all this collides, the capacitor.
So we established that a capacitor stores energy in an electric field. That means its capacitance, its storage capacity C, must be directly proportional to that dielectric constant epsilon r of the insulator between its plates.
Exactly. The better the material is at containing the field, the higher its epsilon r, the more capacitance you get for the same physical size.
Now here's a point of confusion I want to clear up for you. Wait a second. If the dielectric is an insulator, a literal barrier that stops charges from jumping across, how does a capacitor even discharge? Where does that current come from?
That's a great question because it really does seem like a contradiction. The charges never jump that gap. When you discharge a capacitor, the extra electrons that piled up on the negative plate are drawn around the external circuit.
So they flow through the wires, seeking out the positive plate to neutralize the charge.
Exactly. The current you see is just the movement of charge around the outside, trying to fix the imbalance. It acts like a tiny, super-fast battery that stores energy directly in a field, not with chemistry.
That's a fantastic distinction. And the practical side of this is how we combine them with capacitors, if you connect them in parallel.
The capacitance add up. It's the opposite of resistors. You're effectively making the total plate area bigger.
But if you wire them in series, the total capacitance actually decreases.
It diminishes because you're effectively increasing the total separation distance between the outermost plates, which weakens the field containment.
Knowing that inverse behavior is like the first hurdle in any circuits class, but the idea of a perfect capacitor, just those two parallel lines on a schematic, it's a massive lie, isn't it?
It's a lie by omission, for sure. That simple symbol hides a universe of compromises, flaws, and really scary failure modes.
Okay, so now we enter the deep dive on fatal flaws, the non-ideal model. It all starts with parasitic elements, doesn't it?
It does. Every real capacitor isn't just C. It's an equivalent series circuit with at least 3 other components. Equivalent series resistance, or ESR. Equivalent series inductance, or ESL, and a parallel leakage resistance.
Let's focus on the first two, high ESR. That's just that I squared R heat we talked about.
Yeah.
It's just a tiny resistor in series with the capacitor.
Exactly. It generates useless heat, which shortens the component's life, but it also limits the capacitor's ability to do its job, like shunting away high-frequency noise. If the ESR is too high, it's just a poor filter.
And what about ESL? That's the inductance.
ESL is even more insidious. It comes from the physical leads and the internal geometry.
And at a certain frequency, that inductance just takes over.
It does. At what's called the self-resonant frequency, the component stops acting like a capacitor entirely and starts behaving like an inductor. If you're designing for high-speed signals, ignoring ESL means your component might be worse than useless right when you need it most.
Okay, let's get into specific types. Starting with the big ones, the highest risk ones. Electrolytics. Those aluminum cans are everywhere.
They're loved for their high capacitance per volume, but they're hated for their volatility and limited lifespan. Aluminum electrolytics are polarized, and they have this built-in wear-out mechanism of electrolyte loss, or dry out.
The liquid inside just evaporates over time.
It slowly evaporates, especially when it gets hot. This is where that I²R heat from the ESR becomes a killer.
Okay.
The Arrhenius equation in our sources makes this very practical. If you can reduce the capacitor's operating temperature by just 10 degrees Celsius, you can roughly double its expected service life.
Wow. So thermal management is everything for these things.
Everything. And they have that other weird quirk preconditioning. If they sit on a shelf for a year or more, you're supposed to gently power them up.
Why is that?
The dielectric is an incredibly thin oxide layer. If the cap sits unused, that layer can degrade. If you just slam it with its full rated voltage, it could short out. Gradually applying voltage allows that oxide layer to self-repair.
From the slow death of dry out, let's jump to the sudden, spectacular death of the tantalum MnO2 capacitor. You called this one the firecracker.
They are. Tantalum capacitors are incredibly dense. They're used everywhere, but they hide a massive danger. Their construction, it's a finely divided metal powder, tantalum paired with manganese dioxide, is chemically very similar to a pyrotechnic compound.
Wait, similar to a firecracker? That sounds like a terrifying thing to put on a circuit board.
It is. If they fail from overvoltage or a high current surge, they are notorious for failing in a pyrotechnic fashion. They literally explode, they spew flame and smoke. It is not a gentle failure.
So how do designers even use them safely?
Aggressive derating. The safety guidelines recommend derating them by 50% or even more of their rated voltage, just to give them a massive safety margin.
That's a phenomenal example of material science just completely overriding the physics. The math says the voltage is fine, but the chemistry says you can only use half of it.
Exactly. Now let's talk about the most common component on Earth. The ceramic multi-layer chip capacitor, or MLCC.
The workhorse. They're durable, non-polar, low loss. But you said they have the biggest hidden flaw of all.
They do. This affects the cheaper, high-capacitance Class 2 and 3 ceramics, like an X5R type. The datasheet might say it's 10 microfarads, but its actual performance is hugely dependent on the DC bias voltage you apply to it.
So if I buy that 10 microfarad cap and I run it close to its rated 10-volt limit, what am I actually left with?
You could be left with 80 or even 90% less capacitance than what's on the label.
Get out. 90% less.
As the DC bias approaches the rated voltage, the crystal structure of the ceramic is stressed so much that its effective dielectric constant just drops off a cliff.
That is profound. If you're counting on that 10 microfarads for, say, power supply filtering, and you're only getting one, your design is guaranteed to fail.
It is, and they have mechanical flaws, too. They exhibit the piezoelectric effect. They can literally turn electrical ripple into audible noise. They hum.
That's microphonics. And I heard they can crack easily.
They are very brittle. Any board flexure, from assembly or even rough handling, can create microscopic cracks. And unlike a failure that creates an open circuit, these cracks often lead to an immediate and permanent short circuit.
Okay, finally, let's quickly touch on the film capacitors. The durable ones. They at least have one really cool feature.
They do. Reliability. And what's called self-healing. The metallized film types have an electrode layer that's so thin that if a minor fault occurs, the leakage current is enough to instantly vaporize the metal right around the fault.
It clears the short.
It clears the short. They sacrifice a tiny, tiny bit of capacitance to prevent a catastrophic failure. They fail gracefully, which is pretty rare in this world.
It's the ultimate insurance policy, built right into the component itself.
It is.
So we've traveled from the elegant, universal symmetry of Gauss's law all the way to volatile tantalum chips, silently degrading electrolytics, and ceramic chips that might lose 90% of their performance the moment you plug them in.
And the bridge connecting those two worlds is permittivity. I mean, understanding how materials interact with and contain that electric field. That's the key to navigating all these contradictory specifications and failure modes.
The knowledge that saves you from a pyrotechnic failure or a silent performance drop, It's not in the circuit theory textbook. It's in connecting the physics of the field to the chemistry of the material.
So when you next pick up any electronic device, just consider that tiny component, that little ceramic chip or aluminum can. The simplest schematic symbol, just two parallel lines, conceals this whole world of complexity, of stability issues, explosive risks, and silent degradation.
You're holding something that carries the physics of the entire universe within it, yet it's capable of losing almost all of its utility or failing in a flash of fire depending on how its materials were chosen and applied. That tiny symbol is the perfect blueprint for disaster if you ignore the deep dive into what it really is. Join us next time for the deep dive.